Welcome to Physics Chapter 7, Lecture Number 1. In this lecture, we'll cover on your own problems 7.1 to 7.6. The first thing I want you to look at, so open up to page 218 to start. So you also need to have your notes and your calculator, maybe a highlighter as well. So this chapter is about uniform circular motion. Okay, so it's when something travels in a perfect circle, repeatedly passing the same point. So I've left you some space here. I want you to draw out this illustration in the book on page 218 that shows both the acceleration and velocity vectors for uniform circular motion. All right, so if you'll draw these on your notes, I'll explain them while I'm drawing. So let's say we've got an object, and we'll mark that as the radius of a circle. The object, let's say, is traveling counterclockwise. And what I'm drawing here at 4 points, of course there's an infinite number of points, what I'm drawing here would be the velocity vector at these 4 points. So it's straight. What that means is if you let's say you were twirling keys on a lanyard and you were twirling them around and around and around and around and around. If you let them go when those keys were right there, they would travel there, that way, in a straight line. However, what makes it go in a circle like that? Well, it is what we call centripetal force. And those centripetal force vectors at each point on the circle we'll call F sub c. Sorry, I've made it maybe a little too small, but F sub c. Those vectors point inward towards the radius. Okay, so F sub c is what we call centripetal, not centrifugal, centripetal force. Now next to that you have a very similar diagram. Again, let's say we've got keys being spinned around in a circle on a lanyard. Okay, I'm going to draw those 4 velocity vectors again. Now there's more than 4, there's an infinite number. I just don't have space to put an infinite number in. And here's the radius. Just like centripetal force, centripetal acceleration vectors point towards the center of the circle. So A sub c, and I might have said radius, but towards the center of the circle there. So, and we call that A sub c. So A sub c is centripetal acceleration. Okay, so maybe a little highlighting is in order here, just in case those pesky true-false multiple choice type questions show up. Acceleration and force vectors always directed towards the center of the circle, and that center of the circle is just, that's the axis of rotation. The velocity vector is always tangent to the circle. Okay, we've got a couple of equations to memorize. So let's go ahead, put an asterisk by them so you know to memorize it. Centripetal force equation is mass times velocity squared over the radius of the circle. So m is mass in kilograms. V is velocity, and that's usually in meters per second. is radius in meters. Our acceleration equation, a sub c, almost exactly the same thing. It's just v squared over r. Velocity squared over the radius. All right. So now we're ready to start putting these equations in use on solving some problems. So pause the video if you need to. And here we go. So first, let's look at, on your own, 7.1. What the heck? It's a cat hair. On page 223. Right, that says a 1.234 kilogram object travels in a circle at a constant speed of 12.1 meters per second. If the centripetal force applied to the object is 4.67 newtons, what is the radius of the circle in which the object is traveling? Okay, so a lot of times our first problems are just plug and chug type problems, so we can learn the equation. So we have the centripetal force is mv squared over r. We want to know the radius. Well, if you're solving for the one on bottom, you're just going to switch it with the one out front, right? That's our algebra that we learned in chemistry. So r is mv squared over f sub c. So let's just plug the numbers in. The mass is 1.234 kilograms. Velocity is 12.1 meters per second. We don't want to forget to square that. And then our force is 4.67 newtons. All right, if you stick that in your calculator and things don't mess up, you'll have 38.7 meters. All right, how about 7.2 right underneath that one? It says, consider an object moving in a circle at a constant speed. If the centripetal force on the object were to suddenly double but the speed remained unchanged, what would happen to the radius of the circle in which it's traveling? Okay, so this isn't a math problem, it's a logic question. So let's say we have f sub c is mv squared over r. The question asks about the radius. What would happen to the radius? So let's solve for radius. Radius is equal to mv squared over f sub c. This is situation one, but let's say the force were to double. If that's the case, we would have r is mv squared over 2 times f sub c. So this is radius 1. This is radius 2. What would happen to radius 2? It's cut in half, or reduced would be a better way to say that, by half. All right, you just divide the whole thing by 2. So this is a logic question. You just want to solve for letters and then do what the problem tells you to do and then answer the question. So there will be ones like this in the review questions, and I like to put problems like that on the test as well. Okay, let's turn over in our notes to page 2. And this is just a couple of examples from the book. The book on page 224 shows a boy swinging an airplane in a circle tied to a string. And in that situation, what causes the centripetal force? All right, in this situation, what is the centripetal force? What's causing that circular motion? Well, it's the tension in the string. So write in your notes, tension in the string supplies F sub c right next to this bullet. Another kind of common problem is a problem where someone is in a car or on a bicycle. Well, what if you're riding a bicycle in a circle or driving a car, some other vehicle in a circle? What supplies the centripetal force that would allow it to stay in a circle? Well, it's the friction between the road and the tires that supply the centripetal force. So bike example of friction as centripetal force, right in this space, friction between road and tires. Supplies F sub c. All right, so let's work a couple of problems dealing with some a twirling object on a string and a vehicle going in a circle. Okay, 7.3 on page 228 says a child twirls a 314-gram toy airplane around his head. If the 67 centimeter string attached to the plane can withstand a tension of 18.1 newtons, what's the maximum speed with which the toy plane can travel? All right, we are going to have to make a couple of conversions here because newtons, we need mass to be in kilograms and we need the radius to be in meters. Okay, so on your own 7.3 on page 228, we want to know, so we have F sub c is equal to mv squared over r. We want to solve for v squared. Okay, so we're going to multiply both sides by r. So if you do that, you'd have F sub c times r is equal to mv squared, and then divide both sides by m. So we would have v squared is equal to F sub c times r over m. So the velocity is going to be the square root, don't forget it's a vector, of F sub c times r over m. Okay, so we know F sub c, it's 18.1 newtons. We know that the radius 67 centimeters, that'd be 0.67 meters. And then the mass is 314 grams, which would be 0.314 kilograms. So again, with newtons, it's got to be meters and kilograms. And we take the square root of all that. Let's go ahead and practice putting that in our calculator. All right, so the way I would do it is 18.1 times 0.67, then hit enter. Divide that by 0.314, hit enter. And then raise that number to the 0.5 power to take the square root. So that's 6.2 meters per second. Okay, our second problem on that page, 7.4, says a car travels around a curve in the road. If the radius of curvature is 12.1 meters and the car travels at a speed of 21 meters per second, what's the minimum coefficient of friction necessary to keep the car on the curve? All right, so we talked a little bit ago that friction supplied F sub c, right? Okay, so we're going to have friction in this case is equal to mv squared over r. Well, what is friction? We know that friction is mu. In this case, it's mu sub k, but we're just going to say mu times the normal force. Well, what is the normal force? Well, we're on a flat surface, so that's the weight, which is mass times gravity. So friction then is just mu times mass times gravity. So we can substitute that in right there. Mu times mass times gravity is equal to mv squared over r. Well, The masses are both on top on each side, so you can cancel those out. And you would have mu times gravity is equal to v squared over r. Well, we're solving for mu, so we're going to divide both sides by gravity. So mu is v squared over gr. All right, so just a lot of good old algebra here. So the velocity in this problem is 21 meters per second. Do not forget to square it. G is the gravity, 9.8 meters per second squared, gravitational acceleration. And then the radius, 12.1 meters. We didn't even have to make any conversions there. All right, so let's stick that in our calculator. Got 21, let's square that. All right, and divide that by, I'm going to do parentheses, 9.8 times 12.1, hit the right parenthesis, have 3.72. That's a very high coefficient of friction. Much higher than an asphalt is generally about 1. So in order to keep this bike in that short of a radius, going at that speed is going to have to be a lot of friction. So kind of an impractical amount of friction. Right? It's kind of sandpaper amount of friction. Okay, let's pause the video if you need to, and we will keep on going down the notes. Okay, so next in our notes we're going to talk about gravity, the attractive force between two objects that have mass. So they have to have mass. Go ahead and read about Einstein's general theory of relativity, and I will put in the description box a video about general relativity if I can find a good one. But read page 230, the last paragraph. It's very interesting about Einstein, and that paragraph would be potentially on the test. Information from that. So the law of universal gravitation equation. So this is another equation you're going to have to memorize. So write this in that space. That's F sub g is equal to big G. That's the universal gravitation constant. I'll give you that in a minute. Times m1, mass 2, over r squared. Now this part is important. Each object, both mass 1 and mass 2, exerts the same force. So even if one object is small and the other one is huge, one is small and one is massive, they exert the same force on each other. There has to be two to tango here. So defining these, F sub g is the force due to gravity. G is the universal, so you'll write all this in that space in your notes right here, gravitation constant. And that number you do not have to memorize. I'll give it to you. It's 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. That will be given to you. All right, M1 is mass 1. M2, mass 2. And R is the distance between the centers of the two objects. All right, distance between. So, for example, if we have the Earth and the Moon, all right, that radius r is the distance from the center of the Earth to the center of the Moon. Or it could be any two objects. Now this assumes that the orbit is completely circular, which in general it is not exactly that. In a lot of cases it's very close, so we can solve problems. All right, but it assumes a perfect circular motion. All right, and according to Newton, so this is on page 2, we're near the end of page 2. According to Newton, every object in the universe attracts every other object in the universe according to this equation. All right. Another thing is that this might help you on one of the review questions. Write this at the very bottom. Objects must overcome friction to move toward one another. So if you've got a couple of objects on a table or on a whiteboard here, I've got these two, why, they both have mass. Why aren't they moving towards each other? Well, it's because the gravitational attraction, that force, is so small that it's not enough to overcome friction. That's why they're not moving towards each other. If these were really, really large, massive objects, they would move towards each other. They would be able to overcome friction because that F sub g would be large enough. But remember, we're multiplying everything by 6.67 times 10 to the minus 11. So your everyday objects, the force isn't great enough to overcome the frictional force. Okay, so let's move on to page 3 of your notes. We've got a couple of more problems to work and then we'll be done. So, going to do on your own 7.5. Let me go ahead and restate this equation. F sub g is equal to g times m1 times m2 over r squared. All right, on your own 7.5. And there's quite a few pages in your notes to read through. It is absolutely, you should read it on page 234. So that problem says, what is the gravitational force between the moon and the earth? It gives us the mass of the earth, the mass of the moon, the radius of the earth, the radius of the moon, and the distance between the surface of the earth and the surface of the moon. All right, and we're also given big G. Okay. So this is just a lot of big numbers. F sub g is equal to G, 6.67 times 10 to the minus 11. I'm not going to clutter this up with all those units, but it's Newton meter squared per kilogram square. The mass 1, let's say that's the mass of the earth, which is 5.98 times 10 to the 24th kilograms. The mass of the moon, 7.36 times 10 to the 22nd kilograms over the radius squared. Now we have to, again, it's from the center of the earth to the center of the moon. So they're making us work. They didn't just give us the radius. We have to add those three numbers together and then square it. Okay, so that's going to be 6.38 times 10 to the 6th meters. The radius of the earth plus 1.74 times 10 to the 6 meters plus then the distance between the two surfaces, which is 3.76 times 10 to the 8th meters. And then we have to square all that. So a lot of big numbers, easy to mess up in your calculator. So let's go ahead and go through this. And you would expect a pretty big number, pretty big force, a lot of newtons here. Okay. So we've got 6.67 times, okay, I'm not going to do a times here. I'm going to do second function double E minus 11 times 5.98 second double E to the 24th times 7.36 second function double E to the 22nd, and hit enter. And there's our numerator, so we'll come back to that in a minute. Now let's get the denominator. I've got 6.38 times 10 to the 6th plus 1.74 times 10 to the 6th plus 3.76 times 10 to the 8th. All right, that's our numerator. We're going to have to square it. Okay, so what I'm going to do is I'm going to arrow back up here, hit enter, and then divide by, arrow up there, hit enter, but then we're going to square that. All right, and we get 1.99 times 10 to the 20th newtons. Well, you would expect it to be a lot. It's going to take a lot of force to keep the moon moving around the Earth, and these are two very massive objects. Okay, our last little bit in this lecture is circular motion terminology, and we did deal with this a bit in chemistry. So period, which is signified by capital T, is the time. Period is time it takes an object to make one revolution. We did this in pre-cal as well. And the unit is equal to seconds. So time for one revolution. Frequency is the number of revolutions per second. The unit is hertz. All right, so equation here, we have period. In circular motion, it's just the distance over the velocity. You need to remember that. Distance over velocity. Well, what's the distance around the circle? It's the circumference. Over the velocity. Circumference is distance. What's the equation for circumference? Please don't tell me pi r squared. It's 2 pi r over v. So that's the equation for period with a circle. Okay, and then frequency is just 1 over the period. So you need to memorize both of those, 2 pi r over v, and then to get frequency 1. And also another way to do, if you get frequency, the period is then just 1 over the frequency. So if you already have the frequency, you can get period the easy way like that. Okay, let's work on your own. 7.6. Okay, and that is on page 236. All right, it says a child's train moves on a circular track if the train has a constant speed of 1.8 meters per second and the radius of the circular track is 0.81 meters. What is the train's period and frequency? Okay, so we know that period is equal to 2 pi r, the circumference or the distance the train travels, over the velocity. So that's 2 times pi, and the radius is 0.81. Velocity of the train is 1.8 meters per second. So remember, you can use the pi key On your calculator, it's right above the caret, so hit second function and then the caret. But that is 2.83 seconds. So that's how long it takes this toy train to get around the track, 2.83 seconds. Pretty small track. All right, now we can get frequency. That's just 1 over the period. So that's 1 over 2.83. And that is 0.35 hertz. So you could do it 1 over that. That's one way to do it. Another way to do it is sometimes this is the faster way to do it when you have big numbers. You would just type in 2.83 and then hit the x to the -1 button. That's the same as saying 1 over 2.83, and you'll get your 0.35 there. All right, that does it for this lecture. I know this lecture was a little long. But I'm going to link a video in the description box. So watch linked video in description box about gravity. And the homework is review questions, page 248, 1 through 8, and practice problems on page 249, 1 through 6. And that'll do it for this lecture. The next lecture won't be quite so long, and the chapter will be over, just a 2 lecture chapter. So thanks for watching. See you next video.